Hello, and welcome to Systems of Two Equations and Two Unknowns, Part 2. In this part, we look at setting up word problems and then solving systems of equations. We're just with two variables, two equations. It's all good. My name is Tuesday J. Johnson. Yep, forgot my name there for a minute, even though it's on the screen. I'm a lecturer at the University of Texas, El Paso, and an assistant professor at Doña Ana Community College. So word problems, applied examples, models. Basically, it's all the same. Everybody asks, why do we need math? And then we give you word problems, and you say, oh, I hate word problems. Well, word problems are why we need math. We use math to describe the world around us. But in the textbook, and just about any textbook, word problem examples kind of lead you through it. It's like watching Jeopardy. It's somewhere in the, quote, answer, it'll give you what you should ask for the question. So here, in word problem examples, the question or action statement will always tell you what your variables should be. So we'll look at the end of the problem first to get us going. There will be totals or relations in order to give you what your equations should be. So the question or action statement for variables, totals or relations will set up your equations. Always take it slow and think about what you have and how it all fits together. Many times a table makes it easier to organize, but I'll be honest, I don't use a table in this lecture because it's not easier for me, and so it makes it harder for me to explain. But for some people, organizing it out in a table might be the way to go. Alright, here's our problem. Enormous State University, ESU, their math department offers two courses, Finite Math and Applied Calculus. Each section of Finite Math has 45 students, and each section of Applied Calculus has 35 students. The department will offer a total of 55 sections in a semester, and 2,225 students would like to take a math class. How many sections of each course should the department offer in order to fill all sections and accommodate all of the students? So in all of this going on, I focus in on the last sentence slash question. Right? How many sections of each course? So let's let X be the number of finite math sections, and let's let Y be the number of applied calculus sections. Right? Because that's what we're talking about, finite math and applied calculus. How many sections of each course? Let X be the number of sections, let Y be the number of sections. Then I'll go back and I'll ignore what I don't care about. I don't care that there's only two classes. Right? Great, I have that handled, X and Y. Next sentence. Each section of Finite Math has 45 students, and each section of Applied Calculus has 35 students. The department will offer a total of 55 sections in a semester, and 2,225 students would like to take a math class. What I see is there's a total number of sections and a total number of students. So I'm going to write one equation for the number of sections and one equation for the number of students. So our totals tell us what our equations are going to be. So with X is the number of finite math sections and Y the number of applied calculus sections, I can look at students. There are 45 students for each section of finite math, 45X. Plus 35 students for each section of applied calculus, that's 35Y, to give us a total of 2,225 students. I also have a total number of sections. The number of sections of finite math plus the number of sections of applied calculus has to be a total of 55. This is one of those nice systems where if you know how to use substitution method, you should do so. But I'm going to stick with the elimination method. Here we go. Given my two equations, 45x plus 35y equals 2225, and x plus y equals 55, I want to multiply to get the coefficients of either x or y the same, but opposite in sign. And I'm going to choose to make the smaller one, right, 45 compared to 35. 35 is smaller. I'm going to make the smaller coefficients match. So I'm going to multiply the second equation by a negative 35. So that's a negative 35x minus 35y. And negative 35 times 55 is a negative 1925. So I line up my equations. X's over x's, y's over y's, equal signs. and then my constants. 45x minus 35x gives me a 10x. 35y and a negative 35y cancel out. 2225 minus 1925 leaves me with 300. Now, the reason I made the smaller coefficient be the ones that cancel out is just so this is positive. That's it. I like positive numbers. If we divide both sides by 10 here, I end up with x equals 30. Fantastic. If x is 30 and 30 plus y equals 55, it must be that y is 25. Now let's see how that goes with what we have. Well, I know that they should offer 30 sections of finite math because x was the number of sections of finite math, which was 30. Y equal 25 was the number of sections of applied calculus, and I'm able to answer the questions. How many sections of each course? 30 of finite math and 25 of applied calculus. Next example. Anthony is mixing food for his young daughter and would like the meal to supply 1 gram of protein and 5 milligrams of iron. He's mixing together cereal that has 0.5 grams of protein and 1 milligram of iron per ounce, and fruit with 0.2 grams of protein and 2 milligrams of iron per ounce. Again, I always focus on the question or the action statement at the end. What mixture will provide her desired nutrition? Now, the question is not always straightforward. What mixture? In terms of the problem, this is actually saying how much of each ingredient should he use. So let's let x be the number of ounces of cereal, the amount of cereal, and y be the amount of ounces of fruit, the amount of fruit. So x for cereal, y for fruit. Anthony is mixing food for his young daughter and would like, whatever. Not necessary information, that's just the setup. The meal to supply 1 gram of protein, 5 milligrams of iron. These are totals. A total supply of protein and a total supply of iron. So I know I'll have two equations, one that matches up the protein involved in cereal and fruit, and one that matches up the iron in cereal and fruit. So let's focus on each. The protein. 1 gram of protein, which I forgot to highlight in blue. Cereal has 0.5 grams of protein, and fruit has 0.2 grams of protein. So if x is the amount of cereal I use, and the y is the number of ounces of fruit I use, then 0.5 times the amount of cereal plus 0.2 times the amount of fruit should give us my total of 1 gram of protein. Iron. I want 5 milligrams of iron. I know cereal has 1 milligram per ounce, so 1 times the number of ounces of cereal, plus fruit has 2 milligrams of iron per ounce, so 2 times y. I want that to be my total of 5 milligrams of iron. So once I know how to label my variables based on the question, once I know what each equation is going to stand for, protein and iron based on my totals, I could put together the information from cereal and fruit to come up with my system of equations. Now let's solve it. Same equations I had on the last slide. Let's multiply the first equation by a negative 2, right? If I have a half, I multiply a half by 2, I get 1. But I'm going to multiply that by a negative 2. That way I have a positive 1x here. I will have a negative 1x here. I can eliminate my x. 0.5 times negative 2 is a negative 1x. 0.2y times a negative 2 is negative 0.4y. 1 times a negative 2 is a negative 2. Leave my second equation the same. When I add straight down, my x's cancel. They are eliminated. That's what I wanted. 2 minus 0.4 will give us 1.6y. A 5 and a negative 2 gives us 3. And when I divide 3 by a 1.6, I get 1.875. Alright, weird number, but that's alright. We'll go with it. Now from our original equations, I want to solve for x. When I know a y value, I'm definitely going to use the second equation. I'm not going to choose to use extra decimals. So x plus 2 times the y value we just found equals 5. So I multiply. x plus 3.75 equals 5, and when I subtract 3.75 from both sides, I get x equals 1.25. It's always good to identify your variables at the beginning, right? We said x was the amount of cereal, y was the amount of fruit. So we can sum up what we found like this. Anthony should use 1.25 ounces of cereal, that's our x value, and 1.875 ounces of fruit, so his daughter can get the necessary 1 gram of protein and 5 milligrams of iron from this particular meal. Way to go, Anthony. Alright, now turning to one of my favorite topics, sports. The best sports dorm on campus, the Lombardi House, has won a total of 12 games this semester. Some of those games were soccer games, and others were football games, the traditional American football games. According to the rules of the university, each win in a soccer game earns the winning house 2 points, whereas each win in a football game earns them 4 points. If the total number of points Lombardi House earned was 38, how many of each type of game did they win? Now, that's a lot. A whole lot going on there. It all comes down to the question, how many of each type of game did they win? What should our variables represent? How many of each type of game tells us that x is going to be the number of soccer games won, and y is going to be the number of football games. Right? Each type of game. That's how we're going to label our variables. Now, we go back and we see they have a total of 12 games won, and a total number of points was 38. So how should our equations be labeled? Like, what types of equations are we going to have? That's right. We'll have an equation for games, a total of 12 games. So if x is the number of soccer games won, and y is the number of football games won, and that's a total of 12, that's our first equation. Each win in a soccer game will give you 2 points. Each win in a football game will give you 4 points. And we know that they earned a total of 38 points. So we can set up our equations. Alright, so the question tells us our variables. The totals tell us the types of equations, and now we have a system of equations that we can solve. If we have x plus y equals 12 and 2x plus 4y equals 38, I'm going to multiply my top equation by negative 2 so that the coefficients of x's are both 2, one's positive and one's negative. Negative 2x minus 2y equals a negative 24. 2x plus 4y equals 38. When I add straight down, right, the second equation stayed the same. Add straight down, I'll get x's are eliminated. Negative 2y plus 4y is 2y. 38 and a negative 24 is 14. Divide both sides by 2 to get y equals 7 football games. If y equals 7, I can find x to be 5 soccer games. Let's go back to our question and see if we have what we need. How many of each type of game did they win? Lombardi House, which is a shout out to the Green Bay Packers historic coach, Vince Lombardi, which leads me to a shout out to Aaron Jones, UTEP's own, playing at Green Bay currently. They won 7 football games at Lombardi House and 5 football games, soccer games, for my international students there. I do actually know that they're both football. There we go. We've found the answer using system of equations. I know, didn't mean to ruin your sports with math, but there's math all over your sports. Thanks for listening.